This is sample 4, video 3. On my first video on sample 4, I spoke about the important role diatoms play in the environment and in our daily lives. The thing that stood out to me the most was that these organisms are responsible for approximately 20% of global carbon fixation. This got me thinking. Since diatoms utilize inorganic carbon to provide lipids and some oxygen, what do other forms of algae provide us with? To be considered an algae, you must be photosynthetic, and the inheritance of a chloroplast, to me, seems a bit random. One of my first videos was about unicellular flagellates, the Paranema to be specific. They belong to the Euglenozoa phylum. This phylum is characterized by paddle-shaped eukaryotes with 1 or 2 flagellum. Some photosynthetic and some not. The photosynthetic members are the Euglena or Euglenids and can be easily recognized by their bright green color and apparent red eye spot. They are the organisms that are believed to have began the differentiation of plants and animals. Like diatoms, Euglenids convert inorganic carbons to useful intracellular materials. In the diatom's case, it's primarily lipids. In Euglenids, it's proteins. These photosynthetic pathways are so efficient, a study showed that Euglenids' ability to uptake radioactive carbon dioxide and convert it to easily digestible proteins, with little remaining radioactivity. Although this process was facilitated using peroxides and catalysts, it makes you wonder, can an intentional mutation make Euglenids capable of removing radioactive materials? Studies like these are conducted using the Euglena gracilis, a species rarely found in nature. Because of this, they are usually grown in laboratory settings, on a media containing vitamin B12. Their dependence to B12 make them ideal candidates in a clinical setting to determine if a patient has severe anemia. Common euglenids found in nature include the E. viridis and E. sanguinea. These species create green and red algae blooms in stagnant bodies of fresh water containing high nitrogen content. The E. caudata is commonly found in southeast North American regions. They are most abundant in small bodies of water, exactly like the pond I obtained this sample from. Now, let's go to an even smaller scale. Cyanobacteria. Like the name suggests, they are bacteria, not algae. But what you see here is a colony of cyanobacteria densely packed into a filament that secretes a gelatinous material, allowing movement. Filamentous cyanobacteria have always been difficult to classify, and as of now can be divided into 5 orders. With such complex subcategories, I wouldn't be able to fit them all in this video. Because the cyanobacteria share the same filament, they are considered one of the first multicellular organisms. Within these stalks are hundreds upon thousands of individual bacterial cells, communicating with one another, ultimately moving towards the best source of light in an environment. The main purpose of these organisms is the production of oxygen. So much so, they were the cause of the global oxidation event 2,300 million years ago. To this day, marine cyanobacteria contribute to approximately 50% of global oxygen. Cyanobacterial filaments can be found virtually anywhere, acting as an ideal primary producer. Their only limitation is diatomic nitrogen, but they've had plenty of time to evolve under these limiting conditions, with the creation of heterocysts. These specialized cells are sites for nitrogen fixation in environments lacking ammonium and nitrate. Heterocyst-forming cyanobacteria is most commonly found in marine environments. They do, however, have another limitation, and that is hungry microorganisms like ciliates and amoebas. Unfortunately, I haven't captured any filaments being consumed, rather a few organisms lurking around these stalks. Once again, my sources are cited in the description below. Thanks for watching.